There's another thing it's kind of a nuance, but it comes up again and again and again, both in how we do our analysis and in how we structure our attribute tables and the values in the attribute tables, and that's this concept of multipart versus single part vector shape. So I talked about there being a one-to-one correspondence, in this case between a set of boundaries and a state. Problem is when you have a state like Alaska, with all these islands, those are separate little polygons as well as the mainland polygon, how am I going to have an entry for the Alaska when I have multiple polygons for the state? Will I have for each of the bits of Alaska, will I have a different row? Well, we don't want that. We want a state data layer. And the only way we can really do that, or the best way, is to have these multi-part shapes. So there's multi-polygons that make up a feature. Now, Hawaii would be multiple polygons. All the Aleutians and these other outlying islands. And down here in the peninsula, the lower arm of Alaska, there's a bunch of islands. And it's true for a lot of states. Most of the coastal states have many pieces. So there's many barrier islands on the East Coast, or here along the coast of California, there are offshore islands. So you have these multi-part features. And you have to be careful with multi-part features because they look like this. You have multiple geographic entities pointing to one row. This is a multi-part shape, multi-part features. In the table, then, they only have one value, right? So there's a population across all of them. Now, sometimes for some analysis, we want single part shapes. But when we go from multi-part to single part, it means we have to somehow get these attribute values into all these single part shapes, right? So I have 1, 2, 3, 4, 5, 6, 7, 8 main islands in Hawaii. If I go to a single part shape from this multi-part shape, I break it up because I want to look at analysis on the individual islands. I don't have population information for each of them. So often you get the population duplicated for each of them. That is, if you go from multi-part to single part, you get 7 or 8 polygons, so you get 8 rows in the new data layer, and they'll all just have a copy of this population. So we'll get this 1,360,000 for each of the entries. And so if I go on and do another analysis that requires me some data across islands, I can assume it has, or sum to a bigger population. So you have to be careful in this multi-part to single part what happens. Because if I were to map in the first place the population, I would have a different population for each of the islands, right? Some of the islands have 0, some of the islands have, almost 1 million. This is Oahu. And so you get different values depending upon how you create those data. So just be careful of multi-part and single-part conversions because it can mess up the attributes. Usually if you go to single-part to multi-part, you can say I want to sum them, or I want to get some variable that I'll use in the multi-part. But when you go from multi-part to single-part, you're prone to making errors. Just know that that exists. In reality, you want to work as much as you can with the smallest unit of sampling and always maintain a copy of that. So the population data comes from Census Bureau records at the block level. I want to save those data and then make a copy of them and aggregate that. I never want to delete my original data because really what we're doing when we average across an island is just summing all these values, and then we're making one island polygon. There's no way to go back to my original data once I've obliterated the lines. So you got to be careful. We also talk about the concept of vector topology, and we create vector topology for a lot of reasons. The main reason we create vector topology is to make sure when we do some spatial analyses, everything comes together. And the spatial analyses that we're doing is the projection and map transformation I'll talk about next week. When we bend and warp to get from that complexly curved Earth surface to a flat Cartesian surface, we have to make sure the polygons keep their same relative orientation and relative connection. We don't want you to get different neighbors. Your polygons shift, so you have a neighborhood related to somebody else when you go from one coordinate system to another, from the curved Earth surface to a flat surface. And we do topology basically to ensure that. Also for a lot of error correction, a lot of error trapping, a lot of other things, topology is quite useful. So topology is a basically a measure of geometric or construction of geometric constraints that are uniform across bending or warping. They're invariant. And so we have to use this topology to get our data to behave correctly. And we want a special kind of topology called the planar topology because we had adopted this system of layers where everything is in a single layer is compressed down onto the same surface. We can't have one polygon that can be over another polygon. The polygons have to be basically in the same plane. So I don't allow lines to run over lines without having a crossing. It hits the line. There's no way of going over or under. And the same thing with a polygon. You can't lay one on top of another as one placemat on top of another. No, they have to meld together, and the intersection becomes its own polygon. Right? So it's planar, and then everything's forced into a plane. Now, I typically keep track of topology within a layer. I build it and make sure within a layer everything connects correctly, the boundaries are defined correctly, the nodes are at the intersection points. I can also have topology between layers. I have two different layers, and I want to make sure that all the buildings fall within a parcel. Now, buildings, as we know, can cross over parcels. In this case, I can own two lots and build a building that spans the lot boundary. But for the most part, if I'm mapping, and most of the houses are going to fall in a single parcel, I can basically have to flag those where between these two different layers, the parcel layer of ownership and the building footprint layer, it shows me where there's an overlap, and we'll flag this and say, you probably made a mistake here. And then I can also put in exceptions to say, no, this is one of those rare cases where a building is built on two pieces of property, two parcels. So you can use the topology both within layers, which we do mostly, or between layers, right? There's topological data between, in this case, it's a land cover layer and a buildings layer, and here everything matches, so I'm showing the lines of the various land covers and buildings that fit in holes between it. You can have gaps within the layer, so here in this little edge between this concrete pad and the lawn next to it, there's a gap. So I would need to fix that before I go on, because I can't have overlapping or space in a network of, in this case, this data layer. So these are a topological layer. I can also not allow gaps and overlaps among layers. I want to have a complete coverage so that the land cover layer and the buildings layer have no gaps or overlaps between them. I don't have the buildings on top of the land cover layer or with a gap between them, but rather they're harmonized in between them. So I can identify those. And we'll go through in the second and third labs, actually third and fourth labs, building this topology and enforcing this topology rules about them, right? Okay, data and file structures. I'm not going to spend a lot of time on that. We go through it in the book. It's pretty straightforward. It's a reason really why should you care. And the main reason you should care is you're often translating between different softwares, and so the data sets are susceptible to changing your data depending upon how you do that transfer, and sometimes you need to understand a little bit about it. Here's an example of a common workflow. So basically in landscape architecture, I may collect data using a GPS and then interpolate using a program called Surfer, and then do some analysis in Esri, and then output some analysis to this Vectorworks, and then from that into to do some design, some AutoCAD, more design, and then there's some output software, and then into Photoshop. And the data type basically affects how I do this transfer. Same thing in a different analysis. I might do a hydrologic analysis where I have Trimble data collection, and I'm using MATLAB to do some analysis on gradients, and then Surfer, again, to output the results, and then do some more analysis in Esri. And then I use HECRAS, a modeling tool by the Army Corps of Engineers, which will do some outputs that then I'm going to do a time-sensitive modeling with, and then do some more analysis in R to get statistics out of them. And so all this involves a series of data transformations, and they'll ask you questions about bit depth and size and representation and methods for transform. So you have to know something about those. And the main reason you have to know it is that you may have a good output, but if you misunderstand the translation, you get something that looks like this. So you can see how there's some data in there and I can see some structure, but mostly it's gobbledygook. It's noise I created from my good data. One important thing is the kind of data, so how many bits it has, how many bytes there are in those bits, and then how big a piece of data you can store. So we have this binary base 2 notation that we've talked about. In the binary, you can have a binary number, right? And this is 1 byte is 8 bits, so a bit is on or off, and so the number 1 looks like this, and 2 looks like this, right? So there's 3 looks like this. It's like going down our set of columns where the number 11 is 1, 10, and 1, 1, right? So this is the number 1 is basically 1, 1, and 0 anything else. The number 2 is 1, 2, and 0 anything else. The number 4 is 1, 4, and nothing else. The number 5 is 1, 4, and 1, 1. So we're just basically building up in base 2 notation our numbers. If we have 2 or 4 or 8 or 16 byte data, it's different in what it can store than let's say 8 byte data can store less than 16 byte data. So we're going to have an upper limit depending on how many bytes we have. And it would be okay if that's all we did, but we also, for real numbers or for alphanumerics for letters, assign these binary digits differently. And you generally got to be careful about mixing and matching. So if I identify a data layer, a raster data layer as one type, I have to explicitly convert it to another type. I have to be careful about what I combine it with. So there'll be questions about how these things are set and whether you have a sign, for example, whether one of these is a plus or minus sign. And the readings are in the book. It goes through the description or discussion between them. The question is like, which is bigger, this number or this number? Well, clearly the 100 in binary is bigger than the 11 because you have more things to the left. What's the largest number you can store with 8 bits, right? It's 2 to the 8th power, ends up being 256 unless there's a signed bit, right? Which can store more, an unsigned 8-bit or a signed 8-bit, right? Unsigned 8-bit, one of the bits is used in the byte for the sign. So it goes from, let's say, minus 127 to positive 127. 127 is a smaller number than 0 to 256. So you have basically a different range that you can store, and you can store a larger number. These things are important. So I talked earlier about this data and file structures, about the stuff that's hidden underneath. The reason we hide all this stuff underneath is to increase organization, reduce size, and speed access. We have an arc that may be represented by a lot of points. If I end up organizing these points in a way, and then setting pointers between those points and the arcs, and then setting pointers between those arcs and the polygons, I can save space, although you wouldn't think so, for many data sets, rather than having to repeat that line definition a bunch of times. So once for this polygon and once for the adjacent polygon. I can ease updates. Again, I can structure the data so the software can structure the data so it can ease updates so that you can, if you're working on one piece, just isolate that and then rebuild the connections around that one piece. So the data and file structures can be complex. We do some things to organize them, but they're pretty good. There's lots of different file types out there. For example, Esri shape files, or Esri geodatabases, or geopackages. Those are features stored in different structures, but we're trying to represent, for the most part, the same things. They're complicated. You can break your data easily by going in and messing with them. For example, in shape files, there's up to 9 files, usually 3 to 5, that identify all your data. There's this file with an SHP extension that contains the coordinates and a little bit of the topology. A DBF file that contains the attribute data. An SHX file that really focuses on the linkages between the DBF and the SHP among itself. A PRJ, which contains the map projections, something about how the coordinate systems are rendered. There's an indexing file, an SPN, and that can be other files you add. You need all these files intact for the data to be useful, so you can break these data. The same thing, an ArcGeo database is stored inside a directory. If you actually go in that directory and copy or delete or change the name of the files inside that directory, you break it. The same thing with a geo package. So most of these, you just have to be careful to make sure you don't mess with them internally and you keep all the pieces together. The shape files, it's particularly easy to pull just some of the data, so just be careful if you're working with that. And you get to learn about these various data structures. Finally, we sometimes do maintenance on the data to make things easier in display or in transfer. So in the book, we talk about compression, or there's also expansion or pyramiding. In compression, one of them is run length coding, and then run length coding, we say, well, for many data sets, it's more efficient to keep a code or a summary of the number of runs. So there's 2 9s in a row, that shows here, and then 5 6s in a row, and then 1 7 in a row. If I have lots of data that are the same next to each other, here I need 1, 2, 3, 4, 5, 6, 7, 8 bits of information, 8 bytes, basically 8 cells, 8 numbers to store each of these 6s. Here I only need 2. I'm saying it's a run of 6s. There's 8 6s, right? So a run of 8 and the value is 6. So I have 2 bits of information, or 2 pieces of information. And here I have 6 pieces of information. So I can compress the data using run length coding. Now sometimes run length coding hurts in some data sets. All right, these change quite a lot. So here I have 8 values I need to save, and here I have 10 values or 12 values, right? There's 2, 4, 6, 8, 10, 12. So run length coding can result in a bigger data set. The compression doesn't help in this case. In this particular instance, run length coding is good compression when you have large uniform areas for raster data. And remember, these raster data sets can be big. If you have meter level data for the entire state of Minnesota, you have trillions of cells to keep track of. If it's a land cover data area layer, you can reduce the size of your data set from gigabytes or terabytes down to a few megabytes, but only if it's the right kind of data. If it's elevation data or more rapidly varying data, run length code makes the data bigger. There are other compression methods you might use. So I'll stop there. This is just sort of a quick introduction. There's more stuff in the reading, but these are the highlights, the main points, right? You have sort of the real entities or features, you have your data model, and then you have the data structures on them. We work mostly in the data model in that Cartesian or spherical coordinate system. And we'll cover this sort of in much more detail in the next couple of weeks.